The half-life of strontium-90 is 28 years. How long will it take a 50 milligram sample to decay to a mass of 32 milligrams? So because this is a half-life problem, we know that this is going to be exponential decay. So we can begin with our general model for any exponential decay scenario. A is equal to a sub 0, e raised to the r times t power. So remember that a sub 0 is your initial amount. In other words, it's how much you have at time 0. So this problem says that we have a 50 milligram sample. So that tells us that our initial amount is going to be 50 milligrams. So you could begin by setting up your model as A is equal to 50 times e raised to the RT. But at this point, I think it's fairly helpful to go ahead and organize all the information in the problem in a table. So for our model, we're inputting a time, and we're going to then have an output of an amount, a number of milligrams of strontium-90. So if we define our variables, t is going to be time, but let's be more specific. Because our half-life is measured in years, t is going to be the number of years. And then A is the amount of strontium-90, which is going to be measured in milligrams. So A is the number of milligrams. So it says we have a 50 milligram sample, meaning at time 0 we have an amount of 50 milligrams, which we've already used in our model. Now the half-life is 28 years. Remember that this 28 years is a time. So the most common mistake is people sometimes will put the 28 in the wrong side of the table. In other words, they'll put it in for A, but it's a time value, so make sure that you have it here for T. And if the half-life's 28 years, that's how long it takes for our amount to decay to half of what we started with. So if we started with if we started with 50 milligrams, now we have 25. Half of the original amount. And then the question's asking, how long? So how long, it's asking us to solve for time. So we want to know how long will it take for our sample to decay to a mass of 32 milligrams. So here's all of the information organized in a table format. So if you think of this kind of like a checklist, we've already used the 0, 50 for the initial amount. So now we need to go ahead and use the half-life. It takes 28 years for us to have 25 milligrams remaining. So we're basically going to be substituting in the 25 for the amount of strontium, number of milligrams. That goes in for A. Equals 50 e to the r times t, and there's my half-life. My time was, it took 28 years for our quantity to decay down to 25 milligrams. So this is allowing us to go ahead and solve for r. We're solving for the relative decay rate. So we want to start by isolating the exponential quantity. So we want to divide both sides by 50. But dividing both sides of the equation by 50 is going to give us 1/2 is equal to e raised to the 28r power. And remember, this is an exponential equation. So to solve the exponential equation, my preference is to go ahead and rewrite the equation in log form. So if you take the equation and rewrite it in log form, the base of our logarithm is going to be e. So that would be log base e of 1/2, so 1/2 is my argument, is equal to 28r. Log base e of 1/2. But we realize that log base e is equivalent to the natural log. So this is really the natural log of 1/2 is equal to 28 times r. And then dividing by 28 gives us r is equal to the natural log of 1/2 divided by 28. So notice the 28 is not part of the logarithm. It's not part of the argument. We're just taking the natural log of 1/2 and dividing by 28. So here's where you want to go ahead and compute this in your calculator, and then we will store our value so that we're not rounding. We don't want to round this R value. So once you calculate this, it looks like the R value is approximately negative 0.02, roughly. But again, I'm noting that this is a value that I am actually going to store. So although I will write negative 0.02 down on paper, we're going to store this value in our calculator. So please do so. So now we have our model. In other words, we have a function that models the relationship between time and the number of milligrams left in our sample. So our model looks like A is equal to, again, we started with 50 milligrams, so that's 50e raised to the negative 0.02 t power. And again, the negative 0.02 is really going to be stored in our calculator. So here's our model. So now going back up to our table, you can kind of look at your checklist again. We used the 0.50, we've used the 28.25 to allow us to solve for R, and now we're ready to actually attack what the problem was asking for, which was how long will it take for our sample to decay to a mass of 32 milligrams. So now we can go ahead and substitute 32 in for our amount, the number of milligrams, and this allows us to solve for time. So once again, what we're solving right now is an exponential equation. So we have to isolate the exponential quantity. In other words, we need to go ahead and divide both sides by 50. So simplifying that fraction would give us 16 divided by 25. And if you want to convert that to a decimal, you can, as long as you keep it as an exact decimal. You don't want to round in the middle of the problem. You only want to round once at the very, very end of the problem. And now we're ready to go ahead and do the rewrite. So we're going to take this equation, which is currently in exponential form, and we're going to rewrite the equation in log form. So once again, the base of my logarithm is going to be e. That would be log base e of 16/25. That's my argument, 16 over 25, is equal to negative 0.02t. So once we go ahead and divide by the negative 0.02, and we also recognize that log base e is really the same as the natural log, then we'll have the natural log of 16 over 25, all divided by negative 0.02. And now when you go to your calculator to finish the calculation, again, remember that we used, or we are going to use, I should say, our stored value. Rather than typing in negative 0.02, you're going to go ahead and use your stored value, whatever letter you stored that number for. So try that on your calculator, and it looks like you should get approximately 18.03 if we round to the hundredths. 18.03. And remember, that was my value for t, for time. So going all the way back to the beginning, how did we define t? It looks like up here we see that t was time measured in years. So it appears that our answer is approximately 18.03 years. And I always like to stop at the very end of the problem to see if my answer is feasible. So once again, thinking about this in table form, we said that we started at time 0 with 50 milligrams. And then we said that the half-life was 28 years. So it was going to take 28 years for our sample to decay to 25 milligrams. So then just think logically, does our time value make sense? That we got approximately 18 years is how long it would take for our sample to decay to 32 milligrams. So looking here at our A values, seeing that we started with 50, 32 here is right between 50 and 25, so it should make sense that our value of 18 is between 0 and 28, that's a feasible answer, about 18.03 years.